In this lecture video, I'm going to cover how to determine the rate law from a mechanism if your first step is fast. In our previous lecture, we looked at the reaction of 2NO plus Br2 gas to make 2 moles of NOBr gas. And we discussed because this is a termomolecular process, it's unlikely to happen in a single step, even though the rate equals K times NO squared Br2. What we're going to do in this video is look at the mechanism, a proposed mechanism, and figure out the rate law. The proposed mechanism, step 1, NO plus Br2 in equilibrium, and a better way to draw these arrows is really a full arrow in the forward direction and a full in the reverse. These are referred to as equilibrium arrows. What that just means that you have a reaction that is going in the forward direction. You also have a reaction that is going in the reverse direction. We talked about this a little bit in a previous lecture when we were looking at reaction diagrams. We are told this equilibrium is fast. Step 2, NOBr2 plus NO goes to 2NOBr, and we're told this is slow. Notice the slow step is in the forward direction only. The fast step is in equilibrium. Step 1 includes the forward and reverse reactions. Right, so the forward reaction NO plus Br2 is reacting to produce NOBr2. In reverse, we say that NOBr2 is decomposing to produce Br2 plus NO. Okay, so now let's look at this. The rate law for the rate determining step would be, again, this is our slow step. That is our rate determining step. For every single step, we have a rate constant, K1 for the forward, and I like to call K minus 1 for the reverse. And then for step 2, we have this, we'll call K2. So the rate determining step, which is the slow step, rate determining step, RDS, rate equals K2 times NOBr2 times NO. What we notice, I see that NOBr2 is produced in step 1 and consumed in step 2. That tells me that NOBr2 is an intermediate. And intermediates, I'm going to notate with a star, intermediates, you cannot control the concentration of them in the reaction that you're performing in lab. So we need to eliminate NOBr2 from this rate law. Let's write that down. We must eliminate NOBr2 from our rate law because this is an intermediate. Again, we cannot have intermediates in our rate law. We see this as an intermediate, and that tells us we're going to have to go ahead and move forward with the steps to eliminate the intermediate. Let's go ahead and take notes on how to eliminate an intermediate from our rate law. Okay, so how to eliminate an intermediate from the rate law. Step 1, use a previous fast equilibrium step. We can see that NOBR2 is produced in step 1 and used in step 2. And I say in step 1, this is fast. These are equilibrium arrows. So we're going to use step 1 to eliminate NOBR2, our intermediate. I'm going to go ahead and draw a box around here. This is the intermediate that we need to eliminate. So step 1, we're going to use that fast equilibrium step. And what we're going to do next, write the rate of the forward reaction. So here, remember my forward arrow, K1, reverse arrow, K minus 1. So the rate forward equals K1 times NO times BR2. Right, the rate of a forward reaction is always equal to the rate constant K1 times whatever's the tail end of the arrows. Step 3, I'm going to write over here on the left-hand side to give ourselves more space. Write the rate of the reverse reaction. And remember, we're focusing on that rule number 1, use the previous fast equilibrium step, which is indeed the step 1. So our reverse reaction, I'll write rate reverse equals, and again, that's in this direction. So that's K1 times whatever's at the tail end of that arrow, which here is our NOBR2. Step 4. So an important definition of equilibrium is that your forward rate equals the reverse rate. So rate forward equals rate reverse. This is a definition of equilibrium. So we do need to memorize this. It's also the topic of our next chapter. So we're going to write the rate forward equal to the rate reverse. So my rate forward is K1 times NO times BR2 equals my rate reverse, K minus 1. I forgot the minus there. Squeeze that in, K minus 1 times NO BR2. And looking at this, I see it's my NOBR2 that is the intermediate that I'm trying to eliminate from my rate law. Step 5, rearrange algebraically to isolate the intermediate. Which I've designated with a star, our NOBR2. So how do I isolate how do I isolate NOBR2? I want to get it by itself. That means I need to divide both sides by K minus 1. So that cancels. So now I end up just rewriting this NOBR2, which is indeed my intermediate, equals K1 over K minus 1. And remember, K1 is the rate constant for the forward reaction. K minus 1 is the rate constant for the reverse reaction. They are not equal. Okay, K1 is not equal to K minus 1. They're distinctly different numerical values. They do not cancel. So I have NOBR2, my intermediate, equals K1 over K minus 1 times NO times BR2. So now I have a new term to express the concentration of my intermediate. The intermediate is also equal to K1 over K minus 1 NO times Br2. The last step, substitute this new term for the intermediate into the rate law. So on the previous slide, remember, oh goodness, we saw that the rate equals K2 times NOBR2 times NO. That is what we're going to rewrite. Let's see if I can get this back. Maybe I can write it down here. So remember the rate of our slow step. I'm going to just rewrite it. K2 times NOBR2, which is our intermediate, times NO. Now I'm going to write this again. So this will be the rate of our mechanism because we've substituted out the new term for the intermediate. So instead of writing NOBR2, I'm going to write this whole entire term. So the rate of our mechanism, K2, and now instead of NOBR2, I'm going to write K1 over K minus 1 NOBR2. And then the second NO term. So I just zoomed out so I can write this again. So the rate of our mechanism, K2, and now instead of NOBR2, I'm using this entire term. K1 over K minus 1 NO times BR2, and then the last NO, which comes from there. I can rewrite this. So our rate is, just rearranging algebraically to have the numbers in order, K1, K2 over K minus 1, and NO times NO gives us NO squared times BR2. So hopefully this was helpful to learn how to find the rate for a mechanism if your first step is fast and your slow step has an intermediate inside. You'll be following these 1, 2, 3, 4, 5, 6 rules for the other problems. Go ahead and work on some ALEKS problems. I'll do another video to go over the next practice exercise.